What's gamma? This should be plus. It should be this plus that. All right, guys, I'm sorry. I just, you know what happened? I was typing these notes up and I got carried away about how to calculate this. And I forgot, oh, duh, this is also being added here, right? Because the integral around the whole thing should be the residue at I plus the fractional residue at -1, which we worked out here as pi times 1 plus I over 2. So, my apologies. Hopefully, that term came back in the next step. Did it? It did! Hooray! Notice that what? Goodness gracious, I just don't believe anything in here. Shouldn't this be... I think this should be equal... I am annoyed. So I should have that the integral along from -r to r as r goes to infinity, that... Oh, my bad. I'm a dummy. So this integral plus that makes sense. This integral plus that is equal to pi times I minus 1. I'm a dummy. The notes are fine here, except that... Oh no, the notes are fine. I'm a dummy. I'm a dummy. Did I say I'm a dummy? I did, I think. So this is the residue theorem. It is holomorphic. It is holomorphic, so it is just the residue, right? The issue is that when we add up the integrals around the edge of the region, there is the piece around the half circle which goes to 0. There's the two pieces that are horizontal that in the limit become the principal value integral. But there's also this funny little fractional residue term which gets added right here. That's what's going on. And then you subtract to the other side and you've got it. All right, so going back to the more interesting problem, and this is a pretty standard, like, you'll see this a lot of places. This is a popular example. Pretty much anytime anybody talks about Jordan's lemma, the next example they're going to do is the one I have here. So Jordan's lemma gives us a particular estimate. So if we want to integrate sine x over x from 0 to infinity, we can use this indented contour. See, because huh, that's funny. Oh, notice something here, guys. If you use sine z over z, it wouldn't really help you, would it? This is the funny thing, is when you have sine and cosine, direct attack doesn't work. Indirect is what you need. So instead of doing the sine or cosine directly, you look at like integral of e to the iz, because that will pick up a sine x as part of it. And also, so this, on the other hand, also has a singularity at 0, which is interesting. So this has a simple 0 at 0, which is why I have this indented contour. And so what's Jordan's lemma? Jordan's lemma says that the integral of the e to the iz dz is less than or equal to the modulus of e to the iz times the modulus of dz. This is a fancy way of saying arc length integral, all right? Which then gives us pi over r. So notice that this is a little bit better than the rational bound that we've been using, where I insisted on the denominator having degree 2 larger than the numerator. Here we've only got degree 1 larger than the numerator, but because there's an exponential upstairs, and because we have Jordan's lemma, we can still make the ML theorem work for us and make that term go to 0. So the integral of the function around the upper half loop and the limit r goes to infinity goes to 0, and we're just left with the principal value of the integral along the bottom. Now, to calculate that, we're going to have, let's see here. Well, I think that is there any singularity of this inside there? I don't think there is, right? There's the only place this is singular is equal to 0, and that's actually slightly outside. But we're taking the limit as that pinches down on the singularity, which is why even though it's outside, it contributes to the integral around the edge. It's subtle, right? It's subtle. And so So here's the calculation. Let's see here. So we have to take pi I times the res. Now pi I minus pi I, because again it's that clockwise half circle around that. And then this is going to go to 0 because of that estimate up there. And lo and behold, we get this integral is I pi, which gives us, now if we expand this out, e to the ix is what? Well, it's cosine x plus I sine x. So we're actually getting, it's a twofer. On the one hand, we get the integral of sine x over x, the principal value, that's pi, right? Which tells us the integral from 0 to infinity of sine x over x is in fact pi over 2. Notice that actually the singularity for this function at 0 is a removable one for what it's worth. But anyway, so there's that integral. And there's also the integral of cosine x over x from minus infinity to infinity. The principal value of that is what? So there's a real part is cosine x over x. Here, what's the real part over there? It's 0. So the integral of cosine x over x is 0. But we didn't need all this fancy machinery for that. What is cosine x over x? It's a odd function, right? So yeah, of course the principal value of the odd function is 0. But anyway, so there's that one. Now, here's another example where we're using Jordan's lemma. So I'm calculating the integral of x times the sine of 2x over x squared plus 3 from 0 to infinity. As a general rule of order, if you want to get a sine, look at e to the 2iz and an indented contour as needed. Maybe not. Maybe we don't need an indented contour for this one because that's singular at plus or minus I root 3. And so if we do the half circle contour like we just did, we don't even need the fractional residue for this one. We just have, so like this, notice I've got a z squared plus 3. So without Jordan's lemma, we'd be up a creek, but we got Jordan's lemma by faith. And well, I find the proofs in my notes, but whatever. I won't test you on that, obviously. I might test you on applying it, but not on proving it, if that makes sense. So like, anyway, so here, this is less than or equal to that by Jordan's lemma. Well, I guess Jordan's lemma is not yet. Jordan's lemma, this is just the ML theorem, all right? And, or a form of the ML theorem, I should say. And then going from here to here is Jordan's lemma, I believe, because I'm replacing the, well, Jordan's lemma is somewhere in here. I'm not sure where it happened. Oh, down here. I'm an idiot. So right here, integral of I to the z dz is less. This Jordan's lemma is right here. All right. So that's less than pi. So let's see here. I get pi. What about the other one? I'm kind of. I had 2 e to the iz's. What happened to the other one? I am confused. Maybe I do it. Oh, I got a pi squared down here, don't I? So I applied Jordan lemma twice, didn't I? See, to get got the first pi, and then to get another pi. So I just did it 2 times, I think. Where did the e to the I pi go? Well, anyway. I hope you guys get the idea. Let me not talk too much about the details. The basic point here is you pick a contour, which through one of the legs of the contour picks up the integral you're interested in, and then use the residue theorem to calculate the integral around the whole thing, and then take the limit as it gets super large, and that will pick up the integral you're interested in. Let's look at a different problem if I can find it. Exterior domains are fascinating. But I will not test you on them. My apologies. Let's see here. I think it was it mission 8? Well, we talked about this kind of problem in the video. I'm gonna maybe that one. This one is similar to what I did at the start of class. This is not what I'm sorry guys, I can't find it at the moment, but there's this is somewhat similar. So this one's easier than the ones we were just looking at. Why? Kind of easier. Why? Because the denominator is order 2. So I don't need Jordan's lemma for this one. I can just straight, estimate. And this, oh, don't believe this right here. Bogus. Totally bogus. Because do we know A is real? I guess we do. Do we know Z is real? Oof, we don't. So e to the IAZ, not equal to 1, right? This is like the complex version of, in pre-calculus or calculus, somebody's like, it's minus x, so it's negative. It's minus x, so it's negative. Well, what if x is negative? Oops, right? So this is kind of like that. Like, that's my mind not doing well here. To fix that, it's not hard. So if you've got like modulus of z equals to r, you've got you've got z is equal to x plus iy, right? And you've got y is greater than 0 for the contour in question. So what's the modulus of e to the IAZ? How does that go? Well, you've got the modulus of e to the I a times x plus iy, right? What is that? Well, that's the modulus of e to the I ax. Now, a times x is real, for real. And then you've got I squared, which is minus 1, so e to the minus ay, right? So this is straight up e to the minus ay. All right? So while this solution is wrong, it's not really wrong. It's a sin of omission, not commission. So this is what's been omitted. Why is this? How about e to the minus ay? What's the deal with that if a is what? Oh. Yo. Now I'm a little worried. Well, if a is positive, we're good. If a is negative, we're not good. If a is negative, it's very, very bad. But if a is positive, this is what? Less than or equal to 1, right? See, because if a is positive, this is, what's it look like? I'm an idiot. If a is positive, e to the minus ay looks like this, right? So it's biggest if this is y. It's biggest at 1. It's 1 at 0 at y equal to 0, right? And then it drops off. So like, if a is positive, the biggest the numerator can be is 1. However, if a is negative, yeah, that's not right. So what do you do?
Since it's cosine of ax and cosine's even,
yeah,
you just assume it's cosine of absolute value of a times x.
Ah, very good.
Forcing a to be positive in all cases.
Yeah, I think that's good. I think we should do the calculation for the absolute value of a and then use the evenness of cosine to finish the argument. That would be better. There are other problems where you have to like do an integral around the upper half or an integral around the lower half, because think about this. If we were stuck with a being negative, and we had to deal with that. If we were where y is negative, then we can still control that. So sometimes you want to take a contour around the lower half plane instead of the upper half plane if you've got that kind of thing you want to exploit. Have I explained everything there is to know about contour integration? Not even close. Will you be able to learn everything there is to learn about contour integration this semester? There's not a prayer. What should you try to do? It's an art. I'm not an artist. You just try to do the homework problems that I've assigned you, all right? Be able to do the examples that we've done in class and you should be fine. Like, I don't have to be tricky on this stuff. It's tricky enough as it is. Yeah?
Yeah.
And there is more. There is much, much more to learn about contour integration if you're interested. I have some links in the notes, right? But anyway.